Okay, Leslie, can you hear us?
I can.
Yeah, good.
And
Kiki, I think you should let the share screen and set it to the multiple.
Okay.
Okay, all right. So everybody can use that. Okay. That's nice.
Okay.
I'm going to adjust something here.
Can you present? Oh, okay. Okay, let's just open the event first. So welcome everyone. Welcome to the joint atmospheric and planetary science of ITERA, as well as astronomical observatory of ITERA Lampung. We are welcoming Dr. Leslie Young here from Boulder. It's very early there, I guess. It's 1 a.m. there. So it's
12 hours different.
Yeah, it's a very joyous occasion. So everyone, especially the students, need to hear the seminar. Yeah, because she has been waking up very early, or maybe you haven't slept yet for us. And this is to anticipate for the next Pluto Occultations, which will be happening on the 1st of June this year, which hopefully can be observed from Indonesia as well as from Australia. So we welcome Dr. Hakim Lutfi Malasan from Astronomy Observatory of ITERA Lampung.
Thank you very much, Kiki. Good morning, Leslie.
Good morning.
Yeah, and good afternoon to Australia. I see Greg is here, and good afternoon to everybody. Well, I would like to take this opportunity to welcome again Leslie after we've been away for maybe about 11 years, because I made acquaintance with Dr. Leslie Young in 2011. And I soon realized, because I watched I closely watched the study of Pluto, and there were three very important institutions that support this New Horizon probe: the Johns Hopkins University, Southwest Research Institute, and NASA itself. And today we are so lucky to have Dr. Leslie Young, a very leading scientist in this Pluto. And we're going to hear many new things about the Pluto and appealing things. So as you know, that 2006 New Horizons been sent to the outer solar system and keep sending us many heart-breathing picture of Pluto that enables us to see Pluto in its very high resolution. And in 2011, we only have one observatory participated in the occultation, and Mr. Irfan was here on that time. He was the observer with the big CHAIS telescope. And now, as Leslie may see, that there are three observatories are going to join this important occultation campaign observation led by Leslie Young. And I'm happy to introduce Leslie to all of us here. We have Aditya. So Leslie can please raise your hand so at least Leslie can identify you. Yeah. And we have Agus, PJ maybe. Agus, where is Agus? I hope he's here. Yes, Agus Triono is here. Yeah, Leslie, you can identify him. And I'm hoping also the rest, Agus and the group is also here, because we have Irfan, Agus, Yusuf, and perhaps Evan is here also from Bosca Observatory. And last but not least, the National Astronomical Observatory in Timor, represented by Abdurrahman. And of course, I would like to welcome all the participants. So look at here, we have 145 enthusiastic participants who would like to hear a very amazing talk by Dr. Leslie Young. So without any further ado, I'd like to welcome once again Leslie Young and all of our colleagues who come here and the students as well. Thank you very much.
Thank you. So will you share screen and do I share screen and display it myself?
You can just share your screen. It will be no problem.
Okay, beautiful.
Yeah. Can you share your screen?
Okay. So let's see.
Okay.
I am seeing the first screen.
Yes.
And okay, very good. So I am glad for this opportunity, and I am during these 2 weeks also observing in Hawaii. So I'm on a Hawaii night schedule, which puts me at a fine time to give this
Mhm.
talk. So happy to do so. There's a lot of material here because I'm going to cover 3 broad topics. I'm going to talk about a few decades of stellar occultations by Pluto, and I'm going to talk about some of the things we learned from the New Horizons spacecraft, particularly how it relates to Pluto's atmosphere, and then what questions are still open for stellar occultations, and what do we hope to do on June 1st. So any one of these could be an hour-long talk. Please feel free to ask any questions at the end. They've scheduled a lot of time for questions afterwards, so do not be shy. So, talking about stellar occultations, this may be a technique which is new to some of you, so I'm going to go through some detail of what occultations are and how we think about them, 3 different ways to think about them. And what we've then go through a lot of what we've learned since 1988 about Pluto's atmosphere from stellar occultations, that there's something strange in the lower atmosphere, that we want to measure the temperatures in the lower and the upper atmosphere for the energy balance, looking at temperature fluctuations. Is the atmosphere distorted, and how does it change over time? So I stole this next. Okay, hold on. There we go. I stole this next figure from one of the Australian observers, the IOTA, the International Occultation Timing Association. Their manual has a cartoon of what an occultation is for an asteroid. So to occult just means to block. So when an asteroid or a planet blocks a star, it casts a very, very faint shadow on the Earth. So when I say a faint shadow, I mean that the Earth is bathed in all of the glory of the night sky, and then for a few minutes, there's one 12th magnitude star, or 13th magnitude star, which doesn't shine on it anymore. So an extremely faint shadow, but you can picture what's going on if you look at a lunar eclipse. So these are images taken by the EPIC spacecraft of 3 hours of a solar eclipse. So you can see the shadow cast by the moon blocking the sun as the shadow passes over the Earth. So when we talk about the shadow path, this is what we're thinking, what we're talking about, even when we're talking about a faint star and a distant planet. So we spend a lot of time looking at plots like this. So this is how the Earth would look as seen from the star before the target gets exactly in the way, or as if you're sitting on the target, if you're sitting on Pluto looking at the Earth. And the horizontal lines, or the diagonal lines here, are where the center of where Pluto's shadow might pass, and the edge of where Pluto's shadow might pass. And what are the dotted lines? Well, unfortunately, back in 2008, the dotted lines are the uncertainty in Pluto's position. So this shows one prediction using the UCAT catalog and the JPL ephemeris, and another prediction, interesting, shows what where the shadow path would go with the ephemeris that we made ourselves. So I'm going to go back and forth a little bit. You could see that if you're in California, it might be a good day for you if one ephemeris was correct, but you would be out of the shadow path if the other ephemeris was correct. So it's important to figure out where the shadow path went afterwards. And you can do that if you have multiple cuts through the shadow path. So this is an example of the kind of analysis that we do to figure out afterwards the exact geometry of the shadow path. So this is that same occultation, 2008, August 25, my brother's birthday, and I don't know if he made it on to this call, also an observer. So one way to get a quick look is we plot up the flux from the occulted star as blue before it gets blocked by the atmosphere, and red if it gets completely blocked by the atmosphere. And the purple is a radius of half-light. So you can see that you'll want to adjust the east direction and the north direction of Pluto compared to its ephemeris so that you get a match on the half-light. So that's one way of looking at an occultation, thinking of looking at the shadow. You can also think of looking back at the star, which is, of course, how you see it when you're an actual observer. So Pluto is unresolved for most of us. Pluto is only 1/10 of an arcsecond across in the sky. And for most of our telescopes, seeing is probably about an arcsecond. For many of our systems, the pixels themselves are probably about 1/10 of an arcsecond. So before the occultation, you see Pluto and the occulted star separated. And that's very important to measure because you want to know the relative flux between Pluto and Pluto and the star rather, because in an atmospheric occultation by Pluto, the flux from the star never completely goes away. And you want to know, is the bottom of the light curve 5% residual flux, 1% residual flux? If you know what that baseline is, then you can get temperatures on Pluto all the way down to the bottom of your light curve. So you measure Pluto and the star when they're separated. Pluto moves toward the star, and then the flux from the star and Pluto, and also its moon Charon, is all merged together. In the middle of the occultation, the merged light is fainter, and you're left with only the flux from the star. And then after the occultation, you get the merged flux from Pluto and the star again. These images were taken from Sophia press release. So you do your aperture photometry or your PSF fitting photometry, and you come up with a light curve. And this is the one from this June 24th event. Signal noise of 50 per second. I'm going to quote the signal noise averaged over 60 kilometers because that normalizes over whether it was a fast velocity or a slow velocity event, whether you're taking your data rapidly or slowly. It's a way to compare the quality of light curves one to another. So this is what you actually see with your telescope. But if you could look at Pluto with infinite resolution, what would you see? Well, you would see the star approaching Pluto, and then you would see this image of the star creep around, creep around one limb of Pluto, and you would see a secondary star creeping in the opposite direction. This is a diagram from Bruno Siccardi from a 2015 occultation. And this looks a little unbelievable. So I'll just show you an example with real data. So I think I forgot to write down the date of this. I think it was from 2001. There was an occultation by Titan that was observed with adaptive optics. It turned out to be actually a double star. So you can see Titan, very well resolved, and two stars with their area rings because they're diffraction limited with the adaptive optics. If you want to study Titan, in this case, it's easier if you remove Titan from your images. So this is a Titan subtracted image and the same two stars. And if you look at it over time, this is the first star has already done its occultation. This is the beginning of the second star. This faint dashed line is Titan. This is the star is just beginning to be blocked by Titan. And there you see the star is fainter. And as it progresses, the star here creeps around the lower limb, and you get a secondary limb. And here the star continues to creep around the limb, and the secondary image moves in the opposite direction. Then the star comes out of occultation and is a little bright. And here it is at the end of the occultation. So why does it do that? Why does it do such a strange thing? Okay, so this is the third way of looking at occultations. If you have starlight coming in from the left, it encounters an atmosphere and it gets refracted. So most of what we see in stellar occultations is a refraction effect. This explains why you see the star creep around the limb, because even when you're deep in the shadow, you're looking back and you see the image of the star is further from the center of the planet than you are from the shadow center. So here you are, here you are in the shadow plane with your telescope, and here is the planet plane, the atmosphere plane, where the starlight gets bent. Pressure increases as you get closer to the surface, and that means there's a differential in the density. So that bends the starlight more as you get closer to the planet. That causes the light to spread. So that makes it fainter because it defocuses the starlight. And this shows that why we see the two images, one creeping around one limb and the other creeping around the other limb of the planet. From one point, you can get light from either more directly from the near limb or bent and dimmed more from the far limb. So the near limb contribution is dominant. When you're very near the center here, if you have a small enough planet, what happens is you can picture that the ring that is this large radius gets condensed into a small radius near the shadow plane. And so that causes an extra refocusing. And this is what's called the central flash. Sometimes it's very sharp, and sometimes it's more like a bulge like this. Okay, so now I'm going to show you what some of what we've learned about Pluto's atmosphere from occultations. So here I am a year out of college, flying on the Kuiper Airborne Observatory, the KAO. And the point here is that atmospheric occultations fade in and out. An asteroid occultation without an atmosphere will make the starlight blink abruptly out and then blink abruptly back in when it reappears on the other side. But an atmospheric occultation where it is faint because of defocusing fades in and out. On the Kuiper Airborne Observatory, the telescope operator looking at the guider was the first one to notice the slow fade. For the purposes of not dropping any images, we were not seeing the images real time on our actual camera. So that was very exciting. You could say he was the first one to detect Pluto's atmosphere, just because it fades in and out. So we observed in 1988 from 8 locations. A couple other teams observed elsewhere as well. And this is from the KAO, the Kuiper Airborne Observatory. And again, I'm going to quote Singleton noise ratio for 60-kilometer averages. So it ranged from really the quite low signal noise of around 10, and then a few with mid-signal noises of around 40, and the Kuiper Airborne Observatory were 20 to 30, maybe 40. The Kuiper Airborne Observatory had a signal noise ratio for 60 kilometers of a little over 100. So you can look for the radius of half-light at each of those light curves. And you can see here that the ones that had signal noises of less than about 10 really had a hard time pinning down what that half-light is. But Hobart here at a signal noise of 26, very perfectly good. And here's the Kuiper Airborne Observatory. So not very close to the shadow center, but it's still it got this nice deep light curve. Okay. All right, so this is now the mystery of the lower atmosphere. And here again, you can see that the what you actually record is the combination of the merged flux from Pluto and the star. So here's the upper baseline, Pluto plus the star. Here's the lower baseline, Pluto plus the diminished star. And it's tough to figure, you need to figure out what would be the Pluto alone. What is the zero level if the stellar flux went entirely to zero? Because this level here is really a couple of percent above that actual zero level. So what this dashed line is what the atmosphere would look like if the entire atmosphere were clear and close to isothermal. So this is the famous kink at about half light on the Pluto occultation, and it says that the upper atmosphere is consistent with clear and isothermal, and then something is happening in the lower atmosphere, but we don't know what. So this is what we could guess at in 1992, that we didn't even know if the atmosphere was mainly methane or mainly nitrogen. So if it were mainly methane, it would be one temperature. If it were mainly nitrogen, it would be about 100 degrees. And then maybe it goes steeply down to the surface. Or maybe it's 100 degrees and there's a haze layer. And we don't know. We didn't know in 1992 where the radius was. So we didn't know how to connect these. And in fact, we didn't know the radius until the New Horizons flyby in 2015. Okay, so the lower atmosphere mystery continued until the flyby. This is the KO again with the kink at half-light, and a very obvious change in the slope. In 2006, it looks flat, but in fact, if you plot the isothermal fit to the upper part of the light curve, you can see that it deviates. So there's, it would be tempting to look at this and see this even slope and say, oh, the kink is gone. But when you plot it up against an isothermal upper atmosphere, you can see that there's still a deviation in the lower atmosphere. It starts to get different from the upper atmosphere at about 1,200 kilometers. So we started off asking the question, is there haze or a thermal gradient that ends at the surface? And John Stansbury and Emmanuel Lelouch in different papers pointed out that you could have a tropopause as well. So you could have a thermal gradient that stops at the surface, or you could have a mild gradient followed by a tropopause, and it would be subtle. It would be hard to see it. A very steep and a very deep tropopause, you would probably be able to see. So how do you look for haze? Well, one way to look is to look in two different colors. And that was odd because in 2007, we had a dichroic, a blue channel and a red channel, a single noise per 60 kilometers of 80. We didn't see any difference in the amount of flux in the middle, that middle of the light curve in the two colors. But in 2015, with these four colors here going from about 0.6 to 1.8 microns, you definitely did. Now you could say, well, maybe you have to go to infrared to see a big difference, because maybe it's a subtle difference between 0.6 and 0.8 here. The next thing you can talk about is if you have very good signal noise, a signal noise of about 300, you can look to see exactly how the temperature changes by looking at the shape of this very upper part. There's a technique called light curve inversion. Basically, each you are looking at the line of sight integral of the refractivity through the atmosphere. So you do what's called an onion peeling technique or an Abel transform, where you get the temperatures, pressures, and number densities at one layer, and then you go to the next layer in, and you say, okay, we know the pressures and temperatures on the layers above. What does the temperature and pressure on this next layer have to be to match this next point? And then you use that to get the next point below and the next point below. And the one problem is that you have to start off with the temperature and pressure at the very top of your atmosphere correct. And these gray lines show what happens because of uncertainty in the what's called the upper boundary condition. So it isn't until you get to about 1,350, 1,400 kilometers in the atmosphere, a couple hundred kilometers above the surface, that you start to get a handle on what the thermal structure really is. Here is two examples, one from 2015, a data set with a signal and noise ratio of 300 per 60 kilometers. And here's one from 2006. I'm sorry, on this one here, the observation was from 2012. So occultation in 2006 with a signal and noise per 60 kilometers of 333. And you can see the same steep thermal gradient at the bottom, similar temperatures of about 105 or 110, and then decreasing with a small thermal gradient in the upper atmosphere. And here, these lines show, these dashed lines show the convergence of the upper boundary condition. We get spikes in the light curve. And you can see that they're well resolved. We get many image points across them. The main drop is caused by the defocusing of the starlight. If you have temperature fluctuations in the atmosphere, then you also have density fluctuations in the atmosphere, and that can lead to local refocusing. And that's why in the occultation light curve, you see the spikes, and these are very, very subtle in the temperature profile. And they show up more obviously in lots of temperature gradients. Are these related to thermal tides or gravity waves? That was an open question. And then winds. So this is that same Mount John light curve that I showed before when I was talking about Haze. And this shows a model cut through what's called the evolute in a central flash. And if you have an oval atmosphere, an elliptical atmosphere, then you can get these two peaks shown in the black. This comes because the light is bent perpendicular to the, let's see, you draw a line that has constant refractivity, and the light is bent along the refractivity gradient. So it is bent perpendicular to that ellipse. So here are three lines highlighted perpendicular to the ellipse, and they converge on drawing this evolute, this cusp. So if you see the cusp, then that's an indication that something is making the atmosphere non-spherical. So 1988 was that first occultation, and we had to wait until 2002 for the next one. And then Pluto was entering the galactic plane from the point of view of observers on the Earth, and we could get one every year or so. And we saw that the pressure doubled about every decade, even though between 1988 and 2013, in this example, Pluto was passing further from the sun. So why? Let me back up. In 1992, when we published that analysis of what the atmospheric temperature might look like, we did not know whether the atmosphere was mainly methane and mainly nitrogen. After that, we detected nitrogen on its surface spectroscopically. Nitrogen is much more volatile than methane. Pluto's atmosphere is in vapor pressure equilibrium with its surface ices. So seeing nitrogen on the surface meant that the atmosphere was almost certainly mainly nitrogen. In fact, we detected methane, and there was not enough methane to cause the atmosphere we see in occultations. So you have a nitrogen atmosphere, nitrogen ice on the surface. Vapor pressure equilibrium means that you only have to raise the temperature of the surface by about 1.5 degrees to double the pressure. So, so the surface temperature has been increasing by about 1.5 degrees every decade, even though Pluto is moving further from the sun. One explanation right before the Pluto flyby was that the nitrogen at this time was mainly in the northern hemisphere. And so as the subsolar latitude moved to more northerly latitudes, the nitrogen frost got illuminated more directly. And if the thermal inertia was high enough, then you didn't get condensation on the winter pole until quite late. And you never entirely lost the northern volatiles. So this trend was the first indication that Pluto's atmosphere doesn't collapse during its year and that the thermal inertia of the subsurface might be pretty high. So all these decades of occultations set us up with some questions for New Horizons. What controls the atmospheric temperature? Are there winds or waves? What is happening in the lower atmosphere? Are there haze, thermal gradients, tropopause? What's the surface pressure? Big question there, depends on what's the radius. And how does the surface pressure change with time? So to answer these questions, we flew the New Horizons spacecraft. And it has Pepsi and SWAP or plasma instruments, LORI, which is about like an 8-inch celestron, is our main imager. Ralph is our color imager, our wide field monochromatic imager, and our infrared. Alice is one of the 2 main tools for the atmosphere. It's an ultraviolet spectrograph, and Rex is built into the radio system. It's built into the communications, but it also does a radio occultation. And I'm not going to talk much about the dust detector. So just to give you a scale, New Horizons, the antenna is about 2.1 meters. And here I am, I stand at about 1.6 meters. This is the LORI camera here. And let's see. Yes, here's another picture of the LORI camera. And here is the Alice infrared instrument. Okay, so I'm going to start with the surface, because that relates to the atmosphere because of this vapor pressure equilibrium. So if you were looking at Pluto with your own eyes, it might look something like this. A little bit of goldish yellow near the pole, but pretty subtle. So we take our 3 colors and we stretch the contrast so you can see the color variation that this famous heart of Pluto is bluer, bluer on the right ventricle. These dark reddish materials, which are probably processed hydrocarbons. You get a better idea of the composition if you look in the infrared, and there are particular bands that are indicative of frozen nitrogen, methane, or water. You can see the mid-latitudes has most of the nitrogen. The North Pole is dominant in methane. The equatorial or low-mid latitudes has a mixture of methane and water. At the equator, you have both very bright materials that are rich in methane with some nitrogen, and very dark materials which are processed hydrocarbons. And then there is this large basin filled with nitrogen and methane. And this really is a basin. It's a few kilometers below the surrounding surface. So this this completely changes how we think about the behavior of the atmosphere over the course of the year. So before we got to Pluto, we said, well, if there's always nitrogen in the northern hemisphere, then the atmosphere will not collapse, even at its coldest. Well, most of this basin is north of the equator, so this never loses its nitrogen, and so the models after we flew by New Horizons, where we actually saw how the nitrogen was distributed on the surface, those models all agree that it is very unlikely that Pluto's atmosphere will freeze out even when it's far from the sun. So speaking of altitude, here's a nice picture of Pluto's mountains at twilight. So the sun is coming on Pluto, the sun is coming from the top of the image, and there is low-lying haze, and where the mountain tops here interrupt the sunlight, you see the shadow of the mountains cast on the haze near the terminator. Here's on Earth a similar effect. But the haze is more easily seen in the backlit images. So Titan, Triton, and Pluto all have atmospheres with nitrogen, carbon monoxide, and methane, and they all have different kinds of hazes. On Pluto, the haze is layered. If you unfold the images, you can see that they are layered and they are tilted. And why is that? Well, the nitrogen on Pluto gets illuminated by the sun as it rotates. So during the day, the nitrogen sublimes from the surface, and at night it recondenses. So you get, we call it the daily breathing of the atmosphere. So you get these small vertical winds up and down. It's a very small amount of nitrogen, but once you go from the solid phase to the gaseous phase, if you look at what happens over Sputnik Planitia, it's like a piston that sends up about 3 kilometers worth of new cold nitrogen over a day, and then it recondenses at night. So we actually see that this is from the radio occultation using REX, that the atmosphere over Sputnik Planitia has this tropopause from the sublimation over the course of the day. And then places that are over maybe an area which we think might be devoid of nitrogen doesn't have this piston. You just have a temperature gradient going straight to the surface. So, so this question of, is there a tropopause or not? The answer is, well, it depends on whether you're over an area which has nitrogen and whether you're there at the end of the day. Probably if we did this occultation exactly half a Pluto day later, this would have been at the end of a night of condensation, and we might not have this tropopause. So moving on to the ALICE instrument on New Horizons. This is an ultraviolet spectrometer. This is another kind of occultation, a solar occultation, where you watch the sun pass behind Pluto. The spacecraft is so close to Pluto that you don't have enough distance for the defocusing of the starlight to make much difference. This is a case where it actually is absorption, not refraction. So as the sun sets behind Pluto, first at the shortest wavelengths, it gets absorbed by nitrogen. And then as you get deeper in the atmosphere, you get absorption by methane, and then by higher hydrocarbons, C2H2, C2H6, and then haze at the very longest wavelengths. So similar to the onion peeling method of the ground-based stellar occultations, you can use each point above and pick out what is the line of sight opacity and turn that into local density for the different molecules. Excuse me, I'm going to grab some water here. So the nitrogen was hard to do, right? We got the nitrogen just from these two lines. Normally, you would expect to have a fair bit of separation between the methane absorption and the nitrogen absorption to get a deeper measure of the nitrogen. We were surprised by how cold and compressed the atmosphere was. So we did not have much much of an altitude spread where we could measure the nitrogen. So you measure the nitrogen abundance here at the top of the atmosphere. You get the nitrogen abundance from the radio occultation down at the bottom of the atmosphere. And you can tell that you cannot connect these two with a straight line. This black line is what you get from ground-based stellar occultation. So it matches pretty well, but at about 200 kilometers above the surface, you start with the stellar occultation, you start to have the upper boundary condition uncertainty. So that's why this begins to deviate. This dashed line basically, connects the nitrogen profile at the bottom and the nitrogen profile at the top. If you were trying to get a temperature just from the slope of these measurements, you would get a large error bar. You do much better making models that connect the bottom of the atmosphere with the top of the atmosphere. And here you have the steep thermal gradient that we saw in many of the ground-based occultations, temperatures of about 105 to 110. And what we saw in the highest quality ground-based stellar occultations, a decrease in temperature, much more gradual than the steep temperature gradient at the bottom, but a decrease nevertheless. So the ground-based could only get us up to around here, 200 kilometers or so. It wasn't able to say where it started to turn over to be isothermal, what the upper atmospheric temperature is. Upper atmospheric temperature is very cold. Why is there a decrease in the temperature here? Why does it reach about 105? The latest work suggests that it's not the methane thermostat that so many of us had in our minds for so long. So for a long time, we thought that it was heating by methane at 3.3 microns and cooling at 7.7. But it looks now like the haze that we imaged is more effective at both heating and cooling than methane and CO and the other molecular species. So as we, here are the questions that we had in mind as we had the flyby. What controls the atmospheric temperature? Well, maybe haze, but it's really sort of early stages in that work. Are there winds? We couldn't measure winds directly, We didn't see cloud movement, for example, but the hazes are layered, which says that there might be wave action. And we see a tropopause over Sputnik Planitia, which is in line with GCM's global circulation models that have a piston of air rising from this basin of nitrogen during the day and collapsing onto that basin at night. Is there a haze or a steep thermal gradient? That has been one of the key questions for decades. And the answer is, it depends. So yes, we saw haze. Yes, the REX measured a steep thermal gradient. In 2015, the imaged haze probably only has a slant optical depth of 0.05, but does the haze change with time, with location? Is there a tropopause? Again, it depends. We saw it in one place at one time of day, but we only had 2 probes. You know, can we, now that we know what we're looking for, now that we know what the Pluto's radius is, now that we know an example of how quickly the tropopause merges into a stratosphere, can we look for the signature of a tropopause in other light curves? What's the surface pressure now? Well, about 11.5 microbars, or 100,000 times less dense than the Earth's atmosphere. But it depends on local topography. Where the mountaintops are, it's a little bit lower, about 10 microbars. At the deepest places, it's closer to 12 or a little higher. And how does it change with time? The clues from looking at the surface composition and albedos lead to models that suggest that it never freezes out completely. But how much does the nitrogen freeze out on the winter hemisphere? That is a big unknown. So what do we bring from New Horizons that we can try to address with future occultations? Okay, so New Horizons left us with the questions: how do hazes and minor gases control the temperature? When and where is there a tropopause? Is there are there waves in the atmosphere because of tides? What are the winds like, and how does it change? So these are just restating those, but these are particularly addressing the questions that we can try to answer with more ground-based stellar occultations. So now this brings us to why I am particularly here on this particular day. And it's because on June 1st, UT, a pretty bright star, about 13th magnitude, will be occulted by Pluto, and the shadow path is going to pass over southern Indonesia and northern Australia. The dotted line is the predicted center path. The first blue line is around the radius of half-light. And the dotted line is the error. And if you remember back, I showed an example of 2 predictions, one which had occultations in California and one where the edge of the occultation was south of California. And the dotted lines were about a Pluto radius. Now for this one, the uncertainty in what we call the cross track position of the shadow is only about 80 kilometers. So that's very small compared to the radius of Pluto, but it's significant when it comes to the radius of the central flash region. So in the first part of the talk, I showed a lot of light curves and I talked about different signal noises averaged over 60 kilometers. We have a very simple signal to noise estimator. And this star is bright enough that even a 6-inch would give a signal noise per 60 kilometers of about 40. That's similar to the Hobart light curve from the 1988 Discovery occultation. That's definitely good enough for geometry. Maybe a little bit, seeing that it is or is not an isothermal light curve, but we know that it's not isothermal, so that's not a big science driver. But basically, you can help figure out where the shadow passed, even with a very small telescope. 10-inch would be fine, and if the 10-inch were inside the central flash, it would probably detect it. But if you have a 16-inch within the central flash, you could actually measure the shape of the central flash. This is a similar signal noise ratio as that original Kuiper Airborne Observatory light curve. So you can model how quickly the temperature drops from the 105 degrees down to the surface. That is, you can get the gradient of the lower atmosphere, temperature in the lower atmosphere. So with this, if we have several of these in different places, you can see how the thermal gradient, steep thermal gradient in the lower atmosphere compares from place to place. With a 20-inch, it's getting close to being able to characterize the temperatures in the upper atmosphere. In the Kuiper Airborne Observatory, we tried to measure the thermal gradient in the upper atmosphere, and we couldn't get a significant measurement. So this maybe if we have several that are this size or larger, you can combine them to get temperatures in the upper atmosphere. From New Horizons, it looked like once you get above a few hundred kilometers, the upper atmosphere is pretty uniform in temperature. So it might be legitimate to average several together. So what are our plans? Well, we can think about 3 zones. So this line is the central, predicted central flash. The green lines are half light, and the difference between the gray and the green is the 1 sigma uncertainty in the shadow path. So 3 zones, east and west, northern Australia, southern Indonesia, and then north central Australia to map out the central flash. So northwest and northeast Australia, Greg Quick runs astrotourism site in Broome. I believe the plan is to use the 20-inch telescope there. Steve Kerr is right near half-light with a nice light telescope too, 51 centimeters. John Broughton is going to go on the road with his mobile, and that gets us close enough to the center line that you're down below the kink, down below the difference between the clear isothermal, nearly isothermal upper atmosphere and the lower atmosphere with the haze and steep thermal gradient. So he'll be able to not only contribute to the geometry, but maybe say something about the lower atmosphere. In Indonesia, 3 sites. So a couple telescopes at ITERA, including 28 centimeter. At Boscha, they've got their Schmidt telescope and another one as well. Nice size on the Schmidt of 51 centimeters. And at the National Observatory, also another nice large telescope, 50 centimeters. We are going to ship 10 or 12 telescopes. We're arranging with the shippers just this week of finalizing the size of the crates, sizes and weights. And we have sort of 2 strategies here. So as I said, the uncertainty is about 80 kilometers. So we have telescopes spread out, 150 to minus 150 is our plan up along the Stewart Highway. So that the chances will be good that we get 90% chance that we'll get 2 telescopes within the central flash zone. And then we have it more dense, within the center of the central flash zone to increase our chances of getting within 10 kilometers of the center line. We have 2 styles of telescopes. Most of them will be 40 centimeter, 16-inch sky watchers. So these are portable. Here you can see 1 in the foreground and 2 more in the background. These collapse down, and we've taken them all over the world: Senegal, Colombia, Texas, and 2 Hubble optics, one at 51 and one at 61 centimeters, so some good sized glass. Our plan is to deploy these very close to the center line, maybe in Catherine itself, and run them with 2 different filters so that we can not only get some high quality data with these, but also have 2 telescopes co-located with different filters to search for the haze. So how might we do on all of our goals? Can we measure the surface pressure? I believe we'll have good chance because we have cords that are well placed across the whole shadow. So we will be able to reconstruct where the shadow went. That's important because if you only have 1 cord, then there's this ambiguity about did the atmosphere get smaller, or are you just farther from the center line than you thought you were? So with some high single noise light curves and a good distribution across the shadow, we should be able to get surface pressure versus time. Are there waves? We saw some spikes in the Kuiper Airborne Observatory light curve, but most of the light curves that showed spikes had signal noises of about 300. So unless the spikes have changed in character, probably we're not going to be able to see the waves with this particular event. What does the lower atmosphere look like? So we see the difference between the upper and the lower atmosphere at about 900 kilometers of the shadow center. And we have multiple largish telescopes closer than that. So we'll be able to measure that and maybe even compare from one place in Pluto's atmosphere to another. The winds, if Pluto's atmosphere is distorted, then we will get that diamond shape in the very middle of the shadow. And we have telescopes designed to map out that central flash. And how has the haze changed? We're going to approach that by having 2 wavelengths in the central flash. So I'm going to end by saying I've been talking for an hour, but really this project is not me. It's includes the Indonesian and Australian teams, and I will stop there and answer questions. And thank you very much.
Yeah, thank you, Dr. Leslie, for your presentation. It's very important for us to be able to observe the atmosphere of Pluto. Hopefully everyone here already prepared for their observation. So after this, we have a question and answering sessions. Everyone who wants to ask can raise their hand and basically just ask via the video. Or you can also chat or put the questions on the form that I've already shared before. Okay, actually we already have questions on the form. I will send it. So we have questions from Dimas Gilang Ramadan from Pusha Observatory. Why do you use a value of 60 kilometers to calculate SNR? Is it the same value for all observations, or is it depends on the observation location?
Thank you for that question. I did gloss over that. The atmospheric scale height is about 60 kilometers. So that means when you move up about 60 kilometers in Pluto's atmosphere, the atmospheric pressure drops by a factor of E, by about a factor of 3 or so. So the signal noise per scale height is a useful term to use across the solar system. But since today I only care about Pluto, I just use the shorthand of 60 kilometers.
Yeah, thank you. Is this answer satisfying, or do you want to ask more about this, Mr. Dimas from Pusha Observatory? Okay, I assume this is satisfactory. And then the second question also from Mr. Dimas. What do you mean of daily breathing of Pluto's atmosphere? And what's the natural mechanism that causes the daily breathing?
Okay, so there are 4 things that come into the energy balance at Pluto's surface. The smallest one is the flux conducted into and out of the surface. So that depends on the thermal conductivity. That's pretty small. So if you ignore that, the other 3 are all about equal in size. And those 3 are the solar insolation, the thermal emission, epsilon sigma t to the 4th, and the difference between those 2 is made up for by sublimation and condensation of nitrogen. So the latent heat of sublimation. This means that during the daytime, you get an excess of solar heat, and so you end up with sublimation to make up the difference in the energy. And at night, you get no solar heat, and you condense. So it's only millimeter, microns, tens of microns of nitrogen that leaves the surface and re-enters the surface. But that mass of nitrogen is enough to cause, once it turns into gas, it's several kilometers worth of gas. And so the daily breathing is the cycle of the condensation and sublimation of nitrogen.
Okay, thank you. Is this satisfactory, or do you want to ask more questions, Mr. Rimas, about the daily breathing or the atmosphere? While waiting for Mr. Dimas, we have another question. Do you have any plans on? Oh, okay. After this, we will go to Mr. Irfan. Do you have any plans how to get the telescopes to the observing sites yet? I think you mentioned about preparation currently.
So we work with this company called Priority One in Florida. We've worked with them since 2006, and they are wonderful. So we're going to have them trucked to New York for the ones in Virginia, or LA for the ones in Colorado. Then they'll get airlifted probably to Sydney and then trucked to Catherine. So even though the event is not until June 1st, we're need to say goodbye to the telescopes before the end of this month.
Okay, so yeah, hopefully it will go well and arrive there safely in a few weeks, I guess. So after this, we have
actually on that. I do want to say this is part of the reason why the Indonesian telescopes are very important. It's an exciting prospect any year that you do this. But this year, shipping equipment is particularly complicated, and sending travelers across the world is particularly complicated. And it's reassuring to come up with a plan that we can at least measure the pressure just in case something happens. And a few weeks before the event, we learned that we're not allowed to fly to Australia for the central flash. You know, if we know that the Indonesian telescopes in the north and the IOTA observers in the south in Australia, that alone will let us learn about the changing structure of Pluto's atmosphere and its changing pressure.
All right, thank you. I think, I assume, Mr. Renato have another question for you. I hope Mr. Irfan is fine to wait a bit.
Thank you very much. Can you hear me?
Yes.
Yeah. Good day, everyone. My question on how to get the telescopes to the observing sites is more related. How do we get them from Catherine to the different locations? Yeah, it would be very rushed to actually do this in the night. They should be on site during the day, collimated and calibrated. So how do you plan this? Do you get one truck to take everyone to the observing location and then pick them up the next day, or what's your plan?
Right now, the plan is one large vehicle and 2 people per telescope. We can change these a little bit if, you know, we have some people who are extremely talented observers and have been extremely talented observers for 40 years. And this means that we might want to pair them up with young, strong science students from Charles Darwin University, who not only are budding scientists, but also can lift heavy equipment.
Okay, thank you. Is that satisfying enough for you? Or
This is something that we still need to work on.
yeah, I guess
yeah, but
you need to discuss.
Yep.
There should be a feedback from Renato about the weather prospect in Australia prior to making any configuration for the observation, I guess.
Yes, there aren't a lot of roads north-south out of Catherine. So I think we're for the central flash. We may have some flexibility. I know some of so John Broughton on the east coast of Australia says he's planning on one particular beach, but since he's mobile, he can keep an eye on the weather and go inland, which tends to get you drier weather. The fact that we have Broome, Catherine Darwin area, and the East Coast in Australia, maybe that's 3 different locations. I don't know how much the weather tends to be different between your 3 sites in Indonesia. If Bosho is clouded out, will Pang be clouded out too? Or do you sometimes have one clear and the other cloudy?
Yeah, more or less like that. So we may expect, for example, Timor is the driest, but we are in the midst of dry season actually on that time. So we can expect a good prospect. Well, maybe my colleagues from Bosca can add this. So please carry on, Alfia.
Okay, thank you. We also have some sentences from, I guess this is from Greg, I guess. Yeah, in Broome, we will have 2 times 20-inch Kutu-Dobsonian available, as well as 16-inch Skywatcher, as well as the various other 10-inch and up telescope. So we will continue with Mr. Irvan, if you have anything to ask or to say to the forum. And
thank you, Alfia. Thank you, Alfia. Hello?
Yeah, we can hear you.
Oh, yeah. Hello, Leslie. Nice to see you after 2011. I have met John Stansberry and Mark Bullock. They are very yes, good moment for me especially. Just curiosity questions and many other questions also. I just wonder how frequent the occultation of Pluto can be happen, especially that can be observed from Indonesia. When will be the next occultation after June 1st this year?
Oh,
that's
a great question. So between around 2003 and 2015, from the point of view of the Earth, Pluto was passing between the Earth and the galactic plane. So it was passing through very crowded fields, and we had about a good occultation every year, sometimes 2. There was one that happened 2 within 1 week of each other. That was the 2011. I called it the summer of our Pacific adventures because we had telescopes from Baja California all the way to Japan, with places in between like Kwajalein and Majuro Island and Indonesia. The weather and the prediction did not cooperate. So that pair of events was disappointing. Pluto is now in much less crowded fields. So it is, they don't happen as often. On the flip side, we now have the Gaia catalog. And so instead of having uncertainties in the prediction that are 1,000 kilometers, and you don't even know if you're going to get it or not, you have uncertainties that are closer to 100 kilometers. So you know pretty well who is going to be in the shadow path and who is not. So I have not looked ahead 5 years, for example, for the next Indonesian one. But certainly I will be in touch.
Thank you. Thank you.
Okay, I guess that's enough for Mr. Irvan's questions. So yeah, let us know if there will be another one passing by Indonesia. Let's continue with Mr. Agustriano's question. Please, Mr. Agustriano.
Okay, thank you very much for the opportunity. Hello, Dr. Yang, nice to see you. I have two questions. Actually, the first one is about signal to noise ratio. You mentioned earlier in your presentation that we can achieve that certain value of signal to noise ratio. But my question is, in which filters or wavelength that signal to noise ratio is will be achieved? And what do you think about observation without filters? I mean, unfiltered observation. And the second question is about acquisition delay. If we considering that the time resolution is about 0.1 to 1 second, can we neglect the effect of acquisition delay in this matter? Thank you very much.
So unfiltered is fine. Unfiltered gets you a higher signal to noise. And unless you're specifically looking for the effects of haze in the different colors, it's great to go unfiltered. One of the challenges there is that when you go unfiltered, every telescope is going to have a different pivot wavelength. This is a very red star. So to understand the flux ratio between the star and Pluto, it would be good if each telescope can observe a couple hours before or a couple hours after the event to get the separate light curves, separate flux levels. And I didn't quite understand your question about delay.
Acquisition delay. Every system, I think every system has a acquisition delay between when we press the button to record, and then between that to when the data is stored to our drive, right?
Right.
And the typical value, I think, is about 10 to 20 milliseconds, something like that. And considering the time resolution, is it possible to neglect this value?
It would be best if there were some way to characterize that value, and then you can just correct for it. One way that we've done this in the past is if we have a device which can, for example, flash once every second. So you get an LED from a GPS-driven source to make a flash once a second, and you put that somehow into the light path, and then you take images and you see, you know what second, what time the flash happened, and then you see at what time it gets recorded. That's one method of characterizing it. Yes. So 10 milliseconds. The velocity on this event is about 15 kilometers a second. So that would be about 0.1 kilometer uncertainty. So sorry, I'm just thinking here. I'm going back to doing this on the fly. So you want the timing uncertainty to be small compared to your signal, what you would get with infinite signal, with your given signal to noise. So let's say you're running at 10 hertz, 100 milliseconds, and your signal noise per image is 20, then if you had, for instance, a knife edge, right, then your 1 sigma on the location of the knife edge would be a 20th of 100 milliseconds or 5 milliseconds. So in that case, you would want your delay, you would want to be able to characterize your delay to better than 5 milliseconds to not, what's your limit? What's your limit? Are you limited by the signal to noise, or are you limited by your instrumentation? I'm not sure if I'm saying that very clearly.
Yeah, Leslie, may I reiterate what Agus, as far as I understand, Agus is questioning about the how make a compromise between the read time, which is sometimes longer, compared to the issue that you raised about the dead time correction, because the camera dead time correction 10% is intrinsically correct. It's a technical specification of the camera, so right. the decision is to select the best camera for that. But since we deployed a camera with a certain amount dimension of the CCD, it may take some time to read this, even in the inline transfer mode.
Yep. So often we take a subframe. So it's very useful to have a bright star nearby, yep. And there are bright stars about 9 arc minutes away. So a lot of these newer cameras have really pretty big fields of view, and you can subframe as long as you get a good star, because that way you're self-calibrated if you have clouds passing through. And you can choose to go to a slower read rate. 1 second would be fine for getting the overall, well, absolutely fine for geometry, and fine for getting the overall temperature structure as well. We do have, so I know that at least one of your sites has a GPS camera that timestamps the GPS time. And so that's great. That's what we've gone to with our systems as well. Another one of your sites has said, yes, please, we would like to use one of your camera systems. So we'll start working on that, of whether it's best to send a camera ahead of time, whether we need to send a camera and a laptop, or whether you have a computer that can read the data from the camera fast enough.
Yeah.
Or Mark Bullock is able to travel and is happy to come back to Indonesia. If it comes with him, it just goes in his suitcase next to his toothbrush, and we don't have to tell any bureaucrat anything. But if we ship it ahead of time, then we have to fill out all the paperwork to make sure that it doesn't get taken by customs next to all of the snacks that they take as well. So, it sounds like we'll be sending at least one camera, and if we need to send 2 cameras, we only have one Mark Bullock. So if we send 2 cameras, then we'll have to be facing the issue of how to send them to you.
Okay. I guess this discussion will yeah, will be very important for the event because we need to know the exact location and the exact time, I guess. And is there any more questions from the audience?
Yeah, there is in the chat room, I guess.
Wait. So basically, there is another one asking about basically, is there any effects or is there anything happens to Earth atmosphere or to Earth? Yeah, caused by the Pluto's atmosphere. This is by Miss Ajeng from State University of Jakarta.
The only effect on Earth's atmosphere because of the Pluto's occultation is the very small effect that a lot of us get on a lot of airplanes to fly halfway around the world, and perhaps we're contributing to global warming.
Yeah, I guess that's a sad necessity for science. So yeah, I guess there is no more questions from everyone, I guess. So I'm inviting the observatories and all the people who are planning to observe the occultations to have some sentences. Like, for example, we are preparing for this or that or something like that before the Leslie can close the seminar.
I would
Okay.
love to hear that. Yes.
Yeah, you can choose the direction starting from the northeast,
Sure.
northwest to south to southeast. So from ITERA to Australia.
Sounds
Okay.
good.
Yeah, I guess if because we are from Indonesia, if there's
very
anything
good.
from ITERA, so we will start from the last one. Yeah, okay, Mr. Adit.
Okay, hello everyone. In ITERA will try to the best to do the best. Then we hope we can see the transit here with our equipments. So we'll try to be ready, and there are several students who wants to join the team, and they want to study the atmosphere of Pluto.
All right. Can we please hear from Bosca Observatory?
Thank you. We already preparing some equipment. Just as mentioned in Leslie presentation, we are preparing now a smart telescope combined with GSY, GPS, CMOS camera, and then the second one as our backup telescope is GAO ITB RTS. This is a remote telescope system combined with ZWO. Yeah, ZWO 290 mm, and both of them will be in our filter. I think that will cover.
All right, thank you. How are the National Observatory?
Afi,
Yeah. Wait. Okay.
Because there will be a team. So Agus, do you have the team all?
Oh, okay. Yeah. If you have another
I forgot to
team
mention
member
about
ready,
that.
that's also.
So here we have Mr. Yusuf and Mr. Dimas Gilang, and also I don't know, Evan here or not. Let me check first. Oh no, he's not here, and probably Mr. Irfan. Okay.
Yeah,
Okay.
I think Adit missed his group from ITERA.
Yeah, do you want to add about your group in ITERA?
If they are here, it's good.
Mr. Adit? Yeah, there should be. Because we are hosting this, so I assume that they are all here. If the others want to give one or more sentences.
So they are still shy, Leslie.
Yeah. Hopefully, yeah. Okay, yeah.
In ITERA, our Mr. Aditya. There are two Adityas in ITERA, and Ms. Izatul Hafiza and several students from Atmospheric Science and Planetary Science program. There are almost 10 or 15 students who wants to join the program.
Great.
All right, I guess that's it from OAIL or Astronomy Observatory of ITERA Lampung. How about the National Observatory of Indonesia? We should have Mr. Abdurrahman and I think Mr. Abdurrahman. Yeah.
Yeah. Okay. Thank you very much. First of all, thank you, Leslie, for the very nice talk for us. And so we in Kupang are preparing a 50-centimeter telescope. It's a robotic telescope, but we have a problem now with the mounting. So there's a plan to fix the problem next month. So we hope that the telescope will be ready for the event. But of course, we are also preparing for the backup. So we have a much smaller telescope, like the one with 10 centimeter mirror, and also the one with 20 centimeter mirror. Yeah, and the mount for the smaller telescope will also be a robotic mount, and the sensor will be probably a CCD, but since we are not really sure about the whether the system will be fast enough to capture the events, so we are also preparing a CMOS camera, and also maybe Mr. Sungging from Bandung will take other equipment to Kupang also, probably like a scope or a sensor. I don't know if Mr. Kupang is here. Sorry, Mr. Sungging.
Yeah, Mr. Sungging. He's not here. He's busy.
Okay. Yeah, I think that's all. Thank you.
So, thank you very much, Abdul. So Leslie, the best site, in my opinion, for June is in Kupang, because the driest one. And more or less, because you remember in 2011, it was cloudy totally at Bosco Observatory on the last of June. And we are expecting a better weather condition, both in Sumatra as well as in Bandung.
Well, this has been great. And I should mention that there's another occultation group based out of MIT, Massachusetts Institute of Technology in Cambridge, Mass. And they'll be sending some people as well out to Chiruglo in northeastern Australia and Darwin in north central Australia. And I'm not sure what other sites. I don't know if they have plans to send use Sophia. I don't believe so, but I will be talking with them at their morning, which is about 6 hours from now. So I'll tell them how this went and give them the link.
Yeah.
And on which is supposed to be the dry site, my first occultation in Australia and New Zealand, I spent the time before we left watching Lord of the Rings for research purposes, because it was filmed all over New Zealand. And I still think it's unfair that I was clouded out in Rohan and Mark Bowie got data in Rivendell. So, you play the odds.
Yeah.
All right, we have heard from people observing from Indonesia. We also want to hear from everyone in Australia. We can have Greg, I guess, from Broome. That's how to pronounce it, right? Broome.
I don't know if you hear me. Seeing great yet. I'm the observer, so I'll be popping up quickly to Catherine to get involved. It's a little bit unlucky. I'm Leslie could kind of move the occultation in terms of the Mars Observatory in Brisbane is covered by the path, which would be a little more convenient for us all, because the population density in Australia and Northern Territory is outstandingly small. But however, the weather conditions up there are perfect for that time of year. So playing those odds again, you could not be in a better place on the planet for clear skies, nice and warm too. It still only drops to about 16 degrees centigrade at night, and it's not too hot during the day in winter in that area. So that's going to be very, very nice indeed.
Thank you.
Okay. Does anyone else wants to give some sentences from Australia, Mr. Greg or Mr. Steve?
Just from myself, I'll be observing from my backyard, being right in that atmospheric grey zone. Actually, it's the second time I've had an atmospheric grays opportunity for Pluto. An event in 2008 was the same. I'll be using an analog camera, a Wattec 910 BD with a GPS time inserter. It's more sensitive than the CMOS camera I've got. I've got a ZWO 174mm, but I find the Wattec will give a better signal-to-noise ratio at a higher cadence.
Thank you. Okay. Anyone else wants to give one of the sentences on their setup? Okay, we have wait. Okay, we have Mr. Renato. Then after that, we will continue with Mr. Ivan.
Thank you. Best regards from Brisbane, Australia. The logistics for bringing the telescopes on site, I would really suggest we start planning quickly, because I don't believe that there's many car rental places up there that will be able to supply vehicles that can transport 16-inch telescopes in a hurry. Yeah?
Okay.
So sorry for urging you, but if you want to have success, we need to plan ahead.
Right. As you heard, we're right now deciding whether or not to bring 10 16-inch or 8 16-inch, and thinking about the availability of cars in Darwin might be a factor of that. Yes.
Okay, I hope the logistic will be set up. And then how about Mr. Irvan? And I'm inviting for everyone else who wants to observe and talk about the logistic. If not, after Mr. Irvan, we'll ask for another question and have Dr. Leslie to basically close the seminar. Okay, how about Mr. Irvan?
Thank you, Rifa. Excuse me, Pak Hakim. Excuse me, Leslie. As an alumni of observer of Pluto Occultation on June 2011, I think. I would like to motivate younger observers in Indonesia, in northern Australia, northern part of Australia, to use this moment as a great opportunity to create something as enjoyment in your life. Pluto, as before, I just learn about Pluto only from text, only from captured from NASA, only from literature, I think. But after the moment in event occultation in 2011 June with NASA observer, it happened to me. Something happened to me because what? Because I can see Pluto by our telescope. Yes, before the moment, 3 weeks I prepare the telescope. 3 weeks I capture, I spot the star that will be occulted by Pluto. 3 days I looking, where is the Pluto? One night before the moment, the sky is very clear. 1 hour before the moment, one hour before the moment, it happened at 19 local time, 7 p.m. and 8 p.m. and cloudy begin at 7, totally dark. And 2 hours before that, the sky is very clear again. That's good experience for me. And after that, 3 days, 1 week after that, I'm still looking the Pluto. Oh, here we are. Here you are. Here you are. Here you are. That's a good moment for me especially. So I would like to tell everybody here, young observer here, to do this, to use on this this moment to get many experience. And I think it. And in Indonesia at the time, I would like to tell that I would like to tell to Leslie that the visiting of John Cranberry and Mark Bloch in Indonesia in 2011 is also, maybe Pak Kim can tell many more, that also become perhatian publik apa ya? Jadi
he's the public figure on that time. So Leslie, yes, Mark and John was the public figures. So many newspaper reporters came to Bosca to interview them. So if you send somebody down here, so all the reporters will chase him. I guess.
Okay.
Yeah, very nice moment, Van. Yeah, I would like. Thank you. Very good reflection in 2011. It is just we missed the event because of the cloud, but all the preparation, Leslie, was so hard because that telescope is a manual telescope, and believe me, Irfan has a very exceptional skill in moving the telescope to Pluto precisely on that time. So he is the guy on that time.
Very good. Very good.
Good.
Well, your story about when it was clear and when it was cloudy, we have members of the International Occultation Timing Association here who have observed many more occultations even than I have. And they'll all say, you never know about the weather, right? So you don't give up until it really is too late. You know, it could clear up 10 minutes before the event.
Yeah, that's right. Yeah.
Okay. Yeah, that's a very good reflection from Mr. Irfan. So hopefully, with all the logistics, the weather will also permit us to observe Pluto. And we have another talk from Mr. Steph Kier.
Yeah, just a quick question, Leslie. Are you still interested in getting additional people in Australia? I've got a meeting tomorrow afternoon with the Astronomical Association of Queensland, and I just curious as to whether you need more people. It sounds like Greg Quick needs more people. But on your side, Catherine?
Oh, well, we'll be recruiting science and engineering students from Charles Darwin, and we should be able to get as many as we need. But we are short one or two people who are experienced with Skywatchers, especially the 16-inch Skywatchers. So if you have any names of people who could be a lead, you know, them and one or two other people setting up a telescope 15, 40, 70 kilometers from Catherine, we're still short one or two leads.
In all likelihood, there won't be experienced occultation observers, but will be experienced telescope users. So I'll keep that in mind.
Yep. So we can have, we have more people experienced in observing occultations than experienced in these particular telescopes on the US side. So that could be a good pair.
Okay, thank you.
Yeah, I have the same remark with Steve, Leslie, because even last night, one person showed his interest in also participating in observation. I think we'd like to encourage as many as possible amateurs. Of course, we have to let them know precisely the equipment, the requirement for making a successful observation. Then we try to invite them as well.
Yep. When I set up teams, I try to not get them to be too large, because if you have a lot of people that don't have anything to do, then they'll start talking to themselves, and then they'll start talking to the people who need to actually do the work. But it's good to get people involved, and you can always have somebody say, I want you to walk outside every 10 minutes and record how much clouds there are. And then they have something to do. So, but you know that, I'm sure you've done similar things. It's good maybe to have somebody keep track of a timeline. And so their job is to say, okay, in 1 minute, we're going to do this. And in 5 minutes, we're going to do that.
Okay, I think we only have 6 minutes to the scheduled 4 p.m. here. So I guess this is a very
the time flew. This has been great.
Yes, surprise. We have like 1 hour of discussion, which I hope that make everyone's more clear on the setup and stuff. So discussion will definitely be continued even after this, because we still have about 2 months, I guess, but it will also fly by quickly. So we will have a basically last comment from Dr. Leslie Yang. Thank you everyone for basically learn about Pluto's atmosphere together with us here. And basically there is another question, but I think it will be quite hard to answer in this short moment. But if you can basically put it in your final sentence, that will be all right. Especially, is there any spacecraft or Soviet observation this year as well? And is there anything we can do with Pluto's atmosphere in the future? Thank you, everyone. Please, Dr. Leslie Yang.
So I'm not sure if Sophia is involved, but I'll be talking with the MIT group in a few hours, and I'll be sure to ask them. I know that they have some plans to send people on the ground here too.
All right. Is there any other conclusion for this entire 2 hours? And I guess we need a screenshot with everyone. This is a tradition in Indonesian
very
webinar,
good.
so it's pretty interesting. So if anyone can open their cameras, if they haven't already, and wait. Please, Mr. Adit from OAIL to take the screenshot. Okay. So 1, 2, 3. Yeah, smile everyone. Yeah, show your teeth. Okay. How about the others? Yeah, I'm wearing my mask, so you cannot see my teeth.
I don't see you smiling.
Yeah, you can
I
see
could
this.
see it. I could see it here.
Yeah, you can see from my eyes, but yeah.
Yeah, yeah.
Okay. How about the others? Okay. 1, 2, 3. Oh, yeah, Greg is very sunny over there, which is nice, I guess. And then another. Okay, is there enough for screenshot, Mr. Adit? Okay, I assume it is. Okay, is
Mhm.
there any other sentence for Leslie?
Well, thank you very much, Leslie. Thank
Okay,
you for
yeah, thank you.
waking up in the middle of the night.
Yeah, I hope you can sleep after this.
Yeah.
Oh, thank you. It was very good timing that I was giving this talk when I'm on a Hawaii night schedule anyway. And so this is the middle of my workday. this
Leslie,
week.
we have the director of Bosca Observatory. So Dr. Pramana, Nana, please say something. It's like,
Oh yeah,
she is
okay,
here.
yeah.
So remember, in 2011, I was the director, but now Dr. Pramana is the director of Bosca Observatory. So
Thank
thank
you,
you for
Leslie,
coming.
for inviting us to involve in this great endeavor. It's a great opportunity for us. I used to live in Austin, by the way, not very far from where you are.
Oh, very good. Very good. So I'm in the Boulder office, but when you do something logistically difficult like this, we talk to our San Antonio headquarters a lot to make this happen.
All right, yeah.
Great.
Thank you.
Thank you.
Thank you.
Okay, thank you everyone. I guess we already arrived in the end of our very fruitful discussion. And I guess have a nice dinner for everyone in Australia, and I guess everyone in Indonesia who are fasting can also wait for the the fasting break. And I guess Leslie can also take a rest after having 2 hours of talk. Yeah, thank you everyone. I will close the seminar in
Althea.
about 2 minutes.
Yeah.
Thank you.
Thank you.
Thank you.
Bye-bye.
Thank you.
Very good.
Yeah.
Thanks so much.
Bye-bye.
Bye.
Bye.